Relation between angular displacement and its regular counterpart. Let's say a tennis ball attached to a spring rotates about a fixed axis of rotation. The ball rotates in a circle with radius r. Suppose the angular displacement is 3 radians. We want to know that how many meters has the ball gone through. The first quantity that would pop to your mind is linear displacement, of course. If I draw graphically, linear displacement would look something like this. That's a little weird, isn't it? It's weird because of many reasons. Firstly, the arrow represents displacement in this direction, and it must be the velocity, as velocity is the rate of change of displacement and it is in the same direction of displacement. But as the ball rotates, the velocity of the ball is always tangent to the circle, not in this direction. So this concept of displacement causes nothing but just confusion. Secondly, what if I tell you that the tennis ball rotates in a complete circle? What would be the displacement then? It would be 0 because displacement is the straight line distance between 2 points. And technically it shouldn't have velocity, but it does have it as it is moving, so displacement again seems less convenient. Thirdly, to find this direction and magnitude, we'll have to use law of cosines, which is pain in and of itself. Lastly, the consideration of arc length or distance traveled in space by the ball along the boundary of the circle is much more intuitive and easier to find, more convenient, less trouble. Due to these reasons, displacement becomes less intuitive and distance would be more handy to use. Now coming back, the distance that have been covered by the tennis ball is, yes, you know it, 3 times the radius because the angle subtended at the center is 3 radians, and as we know that angle theta in radians is always equal to the length of the arc over the length of the radius, as we have studied previously in the video of radians. By the way, the video is in the tag above. The length of the arc can be represented by L, but in many books, the length is represented by capital S. So I think we should use S as well. So this S is not a vector quantity, but a scalar quantity, and it is the distance covered by the tennis ball in space around the circumference when a certain angle is subtended. So equation can be written as theta equals to S over radius. This equation gives us the relationship between angular displacement and distance. If the angle subtended is theta radians, then radius times theta will give us the arc length traveled by the object. Similarly, if the angular displacement is delta theta, then the distance covered will be radius times delta theta, and the unit of distance is same as that of the radius. If the radius is in meters, then the distance will be also in meters, and if the radius is in centimeters, then the distance will be in centimeters. Let's play with some numbers so that you can understand this better. Consider a tennis ball which is rotating through an angle of 4.5 pi radians and the radius is 2 meters. Then the distance traveled will be 28.26 meters. This equation S equals or distance equals radius times delta theta gives us the translation of angular displacement into its corresponding regular variable. The mathematical proof of this equation is in our geometry course. Check that out as well. In short, any body which undergoes angular displacement of theta radians, then the distance covered by that body would be radius times the angle in radians. And this equation gives us its regular counterpart, that is linear distance. Thank you for watching. Like and subscribe for more such short and crisp educational videos. And also find us on social media platforms at Smartitude Official.